Hey everyone, in this video we are going to be solving for power. We're going to do this in 3 examples, the first of which is lifting an object. Here we go. Link, who has a mass of 60 kilograms, climbs a ladder that is 8 meters tall. He is able to complete this climb in a time of 12 seconds. Solve the power required to make this climb. So if you can solve work, which is what we've been working on, power is just an easy extra step. Because anytime you're solving for power, our power is just equal to the work divided by the time. So all we really need to focus on here is figuring out how much work Link did to climb the ladder, and then divide it by our time, which is 12 seconds. Because Link is lifting an object, that's gravitational potential energy, and we can assume he started on the ground here. So our work is just going to be mgh, mass times gravity times the height that this mass was lifted. So the work that Link did is going to be 60 kilograms multiplied by gravity, 9.81, multiplied by the height of the ladder, 8. Link did work of 4,708.8 joules. Try not to round too early. You might be tempted to round this work off. Don't round until you've finished calculating power. You don't want to round too early. Once you've successfully calculated work, in this case, the work of lifting an object, our power is just going to equal this work, 4,708.8 joules, divided by the time that it took Link to climb the ladder, divided by 12. The power is going to equal 392.4 watts. We measure power in watts, which we can use as a capital W here, but I wanted to write it out the first time just so that you could see it. 0.4 watts. And I apologize for my analogies, but 392.4 watts is about the power needed to run 4 easy bake ovens. So if Link wanted to run 4 easy bake ovens and be cooking those delicious little cupcakes, that's how much power he would have needed to climb that ladder. If he was able to climb the ladder quicker, he would have had a greater power. If he had climbed the ladder slower, Link would have still done the exact same amount of work, but he would have been less powerful. Clearly, the most powerful person of all would be able to just leap up 8 meters in half a second, and then they would have an incredibly high power. Let's go ahead and look at another example. In our second example, we're going to be solving the power of accelerating an object. This is different than lifting an object. This time we're speeding an object up. Here we go. Link uses his bow to fire a 20-gram arrow. When he releases the bowstring, the arrow is accelerated from rest to 80 meters per second in just 0.1 seconds. Let's go ahead. 20-gram arrow. It's accelerated from rest to 80 meters per second in 0.1 seconds. Now, from rest is important because it's going to save us some calculations here. Solve the power of the bow. Again, power is just equal to work divided by time. What we need to do is solve the work. Because this is kinetic energy, and we started from rest, so we had no energy to start off with, our work is going to equal 1/2 mv squared. Now, if you have been studying your work, you will remember that mass has to be in kilograms, and you've been just given a 20-gram arrow. So our very first step here has to be to take those 20 grams, divide it by 1,000 so that it equals 0.02 kilograms. If you forget to do that step, Link is going to have the most fantastically powerful bow you could ever imagine. But we're going to remember to turn that into kilograms. Let's fill in everything that we know to get this work. Our work is equal to 1/2 times the mass of the arrow, 0.02, multiplied by the velocity that we accelerated it to, 80 squared. Now that 80 squared is what's going to make a big difference here. You can go ahead and plug that into your calculator just as is, and what you're going to get is that the work equals 64 joules. So that's all the work that was required to speed up this arrow. The question is, how much power was required? And in order to do that, we need to take into account how quickly we did that work. Power is equal to the work that we did, 64 joules of work, divided by the time that it took to do it. In this case, that bow did all of that work in just 0.1 seconds. So because it did that work really, really fast, the work is going to equal 64 divided by 0.1 for a power of 640 watts, which is about the power to run 6 easy bake ovens. Yay, I like my cupcakes. I like using that as my example. But 640 watts will be the power of this bow in order to accelerate this arrow that quickly. Let's go ahead. We're going to do one more example. In our third example, we are going to be solving the power of pushing an object. Oh, let's go through this one. Link pushes a large block across the floor at a constant velocity as he works to solve a puzzle. Something that Link would do. He pushes with a constant force of 400 newtons and was able to move the block a distance of 5 meters. Solve how powerful Link's push was if it took him 20 seconds to move the block across the floor. Once again, power is equal to work divided by time. If you can solve work, you can solve power. And the work of pushing an object, the equation for that is work is equal to force times distance. This is beautiful because we know the force that Link pushed, it was 400 newtons. So we know it was a force of 400 multiplied by our distance, which is 5 meters, which means the work that Link did in order to push this block across the floor was 2,000 joules of work. As soon as we know the work, we can solve the power. Power is equal to our 2,000 joules for work divided by the time that it took, 20 seconds, which gives us a power of 100 watts. The power exactly required to run one easy bake oven. Now, these are just a few examples of how to solve power. All of these were mechanical, lifting and launching and pushing, but where we've been working with work, these are some great ways in order to calculate the power. I hope that this was helpful for you, and good luck working on your questions. If you have any other questions for me, please feel free to leave them in the comments below. Thank you very much.